Let's now look at a different viewpoint of the variability in the Gauss Markov theorem. So this time we want to look at the mean square of an estimator theta tilde. So let's define the mean square estimation error as the expected value of the difference between theta tilde and the true value, the 2 norm of that squared. Since theta is a vector, we need to find a way of turning it into a scalar. So we take the difference between these two and we find its 2 norm and square it. Now we can decompose this difference as follows. This is a trivial decomposition because these of course add together and we get back to theta tilde minus theta. But by doing this, we can write the mean square error in this form. It's the expected value of the 2 norm of this squared plus the expected value of the norm squared of this thing in here. What's this thing? This is the bias in theta tilde, right? It's expected value minus the true value, right? So we've got the bias and then we've got the 2 norm of that squared and then the expected value of that. Well, this is not random, so it just becomes that. So we've got the bias squared here and this term here. Now the cross terms here, I should have mentioned, are going to disappear when we take this expected value. So what do we have here? Well, we need theta tilde minus theta dot product with itself. So we need this theta tilde minus theta. Right? So theta tilde minus theta is now this thing here. So we've got this time transpose dot product of it with itself. So the whole thing again. Now what are we going to get? So we get theta tilde minus expected value of theta tilde here. And then plus expected value of theta tilde minus theta. Right? Now, this transpose this will give us this dot product. And this transpose this will give us this dot product. So we have this transpose this. So we're going to have theta tilde minus expected value of theta tilde transpose dot product with this thing here, which is expected value of theta tilde minus theta. And we're going to take the expected value of this. Right? And what will happen? Well, the expected value of this minus this is not a random quantity, so we can take it outside. And so we've got the expected value of theta tilde minus the expected value of theta tilde. This is not random, so we just get the expected value of theta tilde minus expected value of theta tilde, which is 0. And similarly with the other cross term. So we're left with only these two terms here. Okay, so where does this take us? Well, we can define this quantity, which I wrote down on the previous slide, that was the first term in that sum. We can define a scalar notion of variance using this quantity. And what is it? It's the second moment of this residual here. Okay, theta tilde minus its expected value. So this is one definition of what we can call total variance for a vector. And let's see if we can simplify it. So I'm defining the variance of theta tilde using this. This is a new definition of total variance. So let's see if we can simplify it. Well, what is it? It's the expected value of this 2 norm squared. So it's the expected value of this dot product. Now this dot product can be written as a trace of this outer product. Right? I'm not going to go through that. It's a fairly standard result, and it's quite easy to see. It's messy, but it's not an especially difficult thing to work out. Just write this out, or take a simpler matrix and just write it out, and you will see that this dot product has to be the trace, what remains along the diagonal, the sum of the diagonal of this quantity here, this outer product. So now we can take this trace outside. So we've got the trace of the expected value of this. Well, what is the expected value of this? This expectation here. This is the covariance of theta tilde by definition. So we've got the trace of the covariance of theta tilde. So this variance, what we've just defined, this total variance, turns out to be the trace of the covariance matrix for theta tilde. So what does the trace measure? In this case, it's measuring a total uncertainty across all coordinates. It's summing along the diagonal, and each term along the diagonal refers to a different coordinate. So minimizing the trace is an alternative way to minimize uncertainty, minimizing the trace or the total variance. And we can even generalize this notion of variance by instead looking at the expected value of this quantity by using any positive definite or semi-definite matrix Q here, in which case the variance we would define as the trace of this matrix Q times the covariance of theta tilde. But okay, let's stick to our case, which is where this is just the identity. So we can now write down a vector bias variance decomposition. The mean square error of theta tilde, any estimator theta tilde, is the trace of its covariance matrix plus its bias squared. So for any unbiased estimator, that bias term will disappear, and we're left with mean square error is simply this total variance, the trace of the covariance matrix. Now, since Gauss Markov minimizes the covariance matrix, it does what? It minimizes, as we've seen before, the variance in every direction, or the variance of any linear scalar summary, or any linear functional. It minimizes the total variance or trace, which we've just shown, and it minimizes the mean square error amongst all unbiased estimators. So these are all equivalent viewpoints, but note that the Gauss-Markov condition is actually stronger than minimizing the trace because that deals with the covariance matrix. This trace minimization is just a scalar summary. It's a weaker concept. Okay, so there is one more interpretation of this, which is related to geometry, but namely that it keeps the noise inside the image space of the design matrix, and it kills all other directions. But we won't bother with that. Okay, I think this is enough.